Let's continue studying conformations of cyclohexane. And this time, I wanted to bring a molecule that actually has a substituent. So here I have, I'm gonna, let's see, doesn't look so good like right now. Okay, this here is the chair, one of the chair conformations of metal cyclohexane. And you see here, I have the model with the metal sticking up, so it is in an axial position. So I'm going to draw this. Let's do that. So I said metal cyclohexane, right? And drawing my chair now, what I had in my hand, remember I had this metal. This is the, say, the central part of the chair. This metal is up, so it is in axial. I am holding it by this corner, right? So drawing my positions, I know that I'm just gonna draw where the actual substituent is. So I'm gonna say this is a metal. Well, better yet, I'm gonna draw explicitly the hydrogens. I think it's shows better what I want to show. And so first, I'm going to do, this was we set in axial. And here we have three metals, let's put it that way. But we know that we have other axial positions. Remember that we have one hydrogen here, I have a hydrogen here, another axial. I have another axial here going down, and this is another up and down. Remember that those alternate. Now let's draw the equatorial positions. The equatorial positions will be slightly down, up, and again, those will have hydrogens, right? We only have this metal substituent. And hydrogen, hydrogen, so down, up, down, up. What I want you to see is that, and it's also seen in the model, notice, the metal here looks like it's kind of bumping is with this hydrogen and also this hydrogen. Now, if you name this carbon, carbon number 1, let's tilt that a little bit. Carbon number 1, 2, and 3. So it's actually bumping with the hydrogen that is in axial in position 3 relative to that. Also with this. And here in the molecule, let's say that I named this 1, 2, 3, but also you could say 1, 2, 3 over to that side. So that interaction causes that energy to be greater in this conformation. So now this is bumping to that. This interaction is called 1,3 diaxial interaction. And then it exists when the substituent is in axial, is greater. Now let's do what we call a ring flip. Now again, starting from this chair, I'm gonna flip, so go to the other chair. And I take this corner up, so this here, I move it up. And now the center is staying the same, I take the other end down. Now notice that now the metal group, which was in axial, is now equatorial. It's this one here. I no longer have those interactions. I do have hydrogen, hydrogen, 1, 3, but I no longer have that interaction with the metal group. So let's draw this chair. So again, you can have this chair, will have the sticking vertical, the metal, that's the chair drawn here. And if I flip it, I will have now the metal in equatorial, and you don't have those type of interactions in this conformation. So let's draw that, the ring flip. This corner that was down, I'm gonna draw up. Then this is, say, the central part. And this was up, I took it down. And so now the metal that was axial is now equatorial, in drawing explicitly or the hydrogens. Now I have the rest of the position, we can draw them all, but we can, in this drawing, omit it. But for now, so that we remember how to draw things, I'm gonna say down. This is my axials, right? Let's do all the axial first. And then down. This is down. This is up. And now I'm going to do my equatorial positions. I'm going to do them in the same color I did before. So now this was equatorial, right? Now it's now equatorial. And this are my equatorial positions now. And so, but what is important is that in the ring flip, the substituent that was here, substituent we call a metal group, right? So the substituent that was in axial here went equatorial in the ring flip. Also, when you have the substituent again here, axial bumping here with this, 1,3, the axial interactions, when it goes equatorial, I no longer have those interactions, and that means this conformation here is lower in energy than this one. So in the equilibrium, there will be more molecules like this with the substituent equator. And so as a conclusion, when we have a monosubstituted cycloalkanes, most molecules will have that substituent in the equatorial position. So the equilibrium is shifted to that side. We're going to do now conformation analysis with more than one substituent in predicting which conformer is more stable.